Hello viewers, welcome back to the course on matrix computation and its application. So in the previous lecture we have started with the one of the definition, that is isomorphism and the inverse of a given linear transformation. So we will continue with that one. Now we are going to define a very important theorem regarding the isomorphism. So it says that every real or maybe complex vector space of dimension n is isomorphic. So it is isomorphic to Vn or Vnc if it is a complex number, but we are talking about the real, so that is there. And this Vn we know that is the nth dimensional vector space. And so from here I can say that if I choose any vector space having the dimension n, then it is isomorphic to Vn. So this one we want to prove. Now for this one, so let I choose that let U be a vector space of dimension n. Now suppose this is the dimension n, then let we also take the set B u1, u2, un and ordered set ordered basis for u. So we are taking the ordered basis of u, and this is of dimension n. Then for any u belongs to u, that I take the vector space u, I just take any element u, we can write u as alpha 1 u1 plus alpha 2 u2 alpha n un. This one I can write because this is the basis, ordered basis. So I can define my element u as this linear combination. And now from here we also know that, so this one I can write equation number 1. So I can write that alpha i's are unique because this is the basis, so it is uniquely determined. Now from here we also know the set, the vector alpha 1, alpha 2, alpha n. So this is the vector is the coordinate vector, is the coordinate vector of u relative to basis B, and we know that this we can represent as alpha 1, alpha 2. So this is a vector, and I can write this as u with the base B. Now from here you know that this vector that belongs to Vn, because it is just the elements coming from the field, so it is a real numbers, so it belongs to Vn. So based on this one we define a linear transformation T from u to Vn, where dimension of u is n, as, so let us say define this one, T of u is equal to alpha 1, alpha 2, alpha n. So, I define like this one, where u I know that I can write the u like this one, and these are the coordinate vectors. So, these are the coordinates alpha 1, alpha 2, alpha n are the coordinates of the vector u with respect to the basis b. So, that we already know. So, this is my 2. So, this is a map that I am defined. Now, we want to show that it is a linear transformation. Now, T is a linear transformation. So, we know that for u belongs to u, I have a u is equal to alpha 1 u 1 plus alpha 2 u 2 alpha n u n. This one I already know. And now, for a element v belongs to u, I can write v as alpha 1 u 1, sorry, I should take this as maybe beta 1 u 1 plus beta 2 u 2 and beta n u n. So, I can write like this one. Now, from here I know that the u plus v is alpha 1 plus beta 1 u 1 alpha 2 plus beta 2 u 2 alpha n plus beta n u n. So, this linear combination I can write, no problem. Now, from here I want to find what will happen T u plus v. Now, T u plus v, I know that from here these are the coordinates of u plus v related to the bases u 1 u 2 up to u n. So, from here I can write that the T of u plus v will be equal to alpha 1 plus beta 1, alpha 2 plus beta 2, alpha n plus beta n. So, this is there. So, now we are finding from here. Now, from here I can write that this vector summation I can write as alpha 1, alpha 2, alpha n plus beta 1, beta 2, beta n, and that gives me, now this is I know that this is equal to T of u plus this is I know from here that the T is v, because if I define the T v, this is equal to beta 1. So, from here I know I got this. So, addition is okay, that this, then also we can define for any alpha belongs to field f, thus it is a scalar, I can show very easily that T of alpha u. So, T of alpha u will be what? So, I am taking the alpha u, u is this one, my u is this one. So, alpha u will be alpha alpha 1 u 1, alpha alpha 2 u 2, alpha alpha n u n. So, from here I can write that this will be equal to alpha alpha 1, alpha alpha 2, alpha alpha n, and this I can take alpha common. So, alpha 1, alpha 2, alpha n, and from here I can say that this is equal to T of u. So, from these two properties we can say that, which implies that my T is a linear transformation. Now, we need to show that T is 1 1. Now, we need to show that T is non-singular, that is 1 1 and on to. Now, from here I want to check. So, let us do this one. T is 1 1. So, this one we need to show. So, for this one, what I am going to do is, so I am going to show here for this one that the null space of T will contain only the 0 element. So, that is what I am going to show you from this one. Now, from here the T is 1 1, because I will take the element T u is equal to 0. So, let us take this element, which implies that I am taking the element alpha 1, alpha 2, alpha n is equal to 0. 0 means it is belonging to the V n, and from here I can get alpha is equal to alpha 1, alpha 2, alpha n, all are 0. So, this is what I have done. Now, from here my u is alpha 1 u 1 plus alpha 2 u 2 alpha n u n, and now I can add this as 0 into u 1 plus 0 into u 2 plus 0 into u n, which shows that my u will be 0, and from here I can say that my T of 0 will be 0, and that shows that this is true. So, from here I can say that the null space will contain only the 0 element, and which implies that T is 1 1. This is what we can show. We earlier also done these things. So, if we are able to show that the null space containing only the 0 element, then this is 1 1. Also, using rank nullity theorem. So, rank nullity theorem says that rank of T plus nullity T. So, that will be, in this case it is of dimension n. So, this is equal to n, but this is 0, and from here I can say that the rank of T is n, and also dimension of, I am taking the space V n. So, the dimension of V n is n, and the rank of this is, so I can say that if the rank is n, it means the range space T is equal to V n, and from here I can say that the range space of T will be complete V n. So, it means the dimension. So, from here I can say that my T is onto. So, T is onto means the whole range space is equal to the complete vector space V n. By the rank nullity theorem we can show this one, because both have the same dimension n n. So, if it is 1 1 onto, then from here we can say that, which implies that the T is isomorphic, and from here I can say that U is isomorphic to V n. If so, that is there, that the dimension of U is n. So, this is a very powerful theorem, because it shows that any, if I choose any vector space of dimension n, then I can define a map which is isomorphic to V n. So, this is the way we can use this theorem. Now, so after doing this theorem, now we want to discuss a very important topic. So, this is what we want to discuss is matrix associated with a linear transformation. So, earlier case also we have discussed the matrices A, and we are sure that that works same as a linear transformation. Now, here we want to give some rigorous idea that how a linear transformation is associated with a matrix. So, this is what we want to show. Now, so how we can check this one. So, let I have a basis B1, suppose I have a basis U1, U2, U3, and I have the another basis V2, that is V1, V2, V3, V4, and these are the be ordered basis of V3 and V4 respectively. Then let there is a linear transformation T from V3 to V4 defined as, so let us we define. So, we are defining the linear transformation, and let the linear transformation is given as T of U1, because I know that the transformation is well defined if it is given on the basis, and that is uniquely determined. So, T of U1 is basically V1 minus 2 V2 plus V3 minus V4. T of U2, that is given to me V1 minus V2 plus 2 V4, and T of U3 is equal to 2 of V1 plus 3 of V2 minus V4. So, this is the transformation given to me. Now, we want to find matrix related to linear transformation T. So, that we want to find out. Now, from here I can define from here that, so this one we can write as, so it is, if you see, it is a linear combination of the basis V1, V2, V3, V4. Now, from here I can write my T of U1 as, because these are the bases, so I can define this as a V1. So, this is my basis, because basis is from V4. So, it is a vector, column vector. So, I just write here V1. So, this is my column vector minus 2 times the column vector V2 plus column vector V3 minus column vector V4, and this is a linear combination we are taking. Now, from here we can write, I can write the coordinates of T U1 with respect to the basis B2, and this is what, this is equal to 1 minus 2, 1 minus 1. So, this is the basis we can define, the coordinates of the given element T U1 with respect to the relative basis B2. Similarly, I can define T U2 with respect to the basis B2. So, that will be a 1 minus 1 0 2, and T of U3 basis B2. So, this will be 2 3 0 minus 1. Now, these are all the coordinates we have defined corresponding to the different vectors. Now, what I do, I write a matrix with these coordinates. So, I am writing the first coordinate as a first column. So, if you write this one, I can write the first coordinate as 1 minus 2, 1 minus 1. So, this is the first coordinate I am writing. The second coordinate 1 minus 1 0 2, 1 minus 1 0 2 and 2 3 0 2 3 0 minus 1. So, this is a matrix we are getting, this is 4 cross 3 matrix, and I call it this matrix A. So, this is the matrix is called the matrix of linear transformation T relative to the basis B1 B2, because here we are taking the basis B1 and B2, and this is we are taking ordered basis. Why we are taking ordered basis? Because we are using the corresponding coordinate vector. So, that is why if we change the order, the coordinate will change. So, that will be a different vector in that case. So, this is the corresponding matrix we are able to define. So, now from here we can write that. So, I can define the definition now. So, what do we say in this definition? Let U and V be vector spaces of dimension n and m respectively. So, this is the vector spaces of dimension n and m, that is respectively. Let, so I take B1 the basis that represent U1, U2, Un. Let B1 and B2, that is V1, V2, Vm, because it is a dimension m, be ordered basis for U and V respectively. Then let there is a linear transformation T from U to V, it is given to me. So, let T is equal to U to be a linear transformation. So, it is given to us, this is a linear transformation defined as, so it is defined like this one, T of U1, because it is going from U to V, that is equal to, maybe I can call it alpha 1 1 V1 plus alpha 2 1 V2 plus alpha 3 1 V3 plus alpha. So, because we have a m number of vectors here, so it will be m1 Vm. Similarly, I can define my T of any uj. So, it will be alpha j1 V1 alpha. So, it will be 1j alpha 2j V2 alpha mj Vm, and in the end it will get T of Un, this will be alpha 1n V1 plus alpha 2n V2 alpha mn Vm. So, this is the linear transformation is defined to me. So, it is defined by Leaks 1. Then the matrix associated with the linear transformation LT is given as. So, if you see from here, then this linear transformation we can define uniquely, because these are the bases, and if it is the basis, then we know that the corresponding system of equation will be the system will be non-singular, and then we can define the unique solution for that system. So, in this case, all this alpha 1, alpha 2, all these elements will be unique and it will be uniquely determined, and so this linear transformation will be unique. So, then the corresponding matrix A, so I give the name A. So, this can be given as, now what we are going to do, I am taking the first element and putting its coordinate as the first column. So, it will be alpha 1 1, alpha 2 1 up to alpha m 1, because m is number. Then I can define alpha 1 2, alpha 2 2, alpha m 2. So, it is alpha, I can define from 1 1, so 1 n, alpha 2 n and alpha m n. So, we are defining the matrix of order m cross n. So, this is the matrix that will be, so this is the matrix A. So, the matrix associated with the linear transformation is given by this one and is called matrix associated with linear transformation LT related to basis B1 and B2, and we also sometimes represent by T transformation corresponding to B1 B2, that is equal to my matrix A. So, this basically matrix is made up of the coordinates of this one, coordinate of the vectors. So, this way we can define the matrix associated with the linear transformation. So, let us take one example. Let a linear transformation T from V2 to V3 is defined as T of x1 x2 is equal to x1 plus x2, 2x1 minus x2, 7x2. So, this is a transformation given to me. It is from V2 to V3. Then find the associated matrix A. So, we need to find the matrix A, but we need to find the basis. So, find the associated matrix A related to standard basis. So, related to standard basis means I know that the standard basis B1 is E1 and E2 and B2 is, I just call it maybe F1, F2, F3. you know that this E1 is basically 1 0, E2 is 0 1, F1 is 1 0 0, F2 is 0 1 0, and F3 is 0 0 1. So, these are the standard bases. Now, from here, so how we can find this solution? So, in this case I just define now, because we deal with the standard bases. So, if you see from here, I can write here as x1 x2, and this one I can write x1 common. So, it will be 1 2 0 plus x2, it is 1 minus 1 7. So, now from here we can define this transformation. We can write like this one. Now, from here, if you see from here, then I can write this as 1 2 0 1 minus 1 7. This is the matrix, and here it is x1 x2. Now, this is equal to T of x1 x2. x1 x2 is the vector. Here I am writing in the terms of a column vector, because here it is a matrix 3 cross 2. So, it is 2 cross 1. Now, based on this one, if you can see from here, then this matrix A will correspond to linear transformation T, because in this case I am talking about the standard basis. So, standard basis means no change will be there in the terms of coordinates, because we know that, because I can write my element 1 2 0 can be written as 1 F1 plus 2 F2 plus 0 F3. So, there is no change in the coordinates. So, that is why I am able to write the matrix directly from here. It is 1 2 0. Similar to the second one. So, the second element is 1 minus 1 7. I can write in this form. So, from here you can see that this is a linear corresponding matrix to the linear transformation T. So, my matrix will be in this case. So, my A will be 1 2 0 and 1 minus 1 and 7, and this will be always 3 cross 2, because our transformation is from V2 to V3. So, this is my corresponding matrix, so related to the standard basis. So, this is the matrix related to standard basis. So, that is we can define with the corresponding to standard basis. Now, if somebody says me that define the linear transformation, we have a transformation, the same transformation, but I change my basis, then what will happen to the matrix? So, that matrix we can define. So, this type of things we will do in the next lecture. So, we will stop here. So, in the today's lecture we have defined that how for a given linear transformation, how we can show a matrix corresponding to the linear transformation related to the given basis, and in the coming lecture we will continue with this one. So, thanks for watching, thanks very much.